All right, so in order to talk about chemical energy transform and movement in different systems, we have to think about a frame of reference and really the introduction of energy flow in terms of convention. And we've already alluded to this in previous videos, but we haven't given it a real formalism. And when I talk about the illusion, what we talked about was that positive changes in energy, those were in increase in the system energy. And we said that negative changes in energy were releases of energy. And we said the release of energy was net stabilizing because you're going from a higher energy state to a lower energy state, sort of going from here to here. And we always know the universe always wants to go from high energy to low. So we noted this as a negative delta E. And we said the opposite of that, if you wanted to traverse back up this hill from this state to this top state, that would be a positive delta E. And we would have to somehow come up with that energy and put it into the system. Okay, so we're talking about positive and negative. What are we referring to? Well, if we're talking about negative as the release of energy from what? That requires us to define this convention of the system and the surroundings. And so the system is the thing you are studying, or it's the thing that you're taking the perspective from. So if we're talking about energy flow, in terms of positive and negative, we're thinking about it from the perspective of the system. That system could be an Erlenmeyer flask full of chemicals. It could be the coffee in your coffee mug that you're drinking. It could be anything that you are defining as the system. And then everything else that is not that thing that you are evaluating is the surroundings. That could be the coffee mug itself. It could be the entire universe. And so when we're thinking about the direction of energy flow, if we're thinking about a negative direction, as indicated by the going downhill here, we're saying that the system is decreasing in energy. So this would be from the perspective of the system. So the system is decreasing in energy. And if the system is decreasing energy, that means there's a release of energy from the system as heat. Where does that energy go? Well, it has to go to the surroundings, right? It has to. All energy is conserved, so energy has to be just transformed to something else. And in this case, it's leaving this Erlenmeyer flask, and the final energy is less than the initial, right? The opposite is true from the perspective of the system. If we have a positive change in delta E, so that's starting at some initial energy and ending at a final energy, which means we're having to put energy into the system. Where does that energy have to come from? Well, it has to come from the surroundings, which is what's happening here. We've got to steal energy from the surroundings and absorb that into the system to get it to move from its initial state up to a higher energy state. So we're always thinking about energy transfer from the perspective of the system and its relationship to the surroundings. So let's think about that with a real chemical reaction, the same one that we introduced the previous video with. So when we think about the burning of methane or natural gas, that itself is the system. This chemical reaction here is the system itself. And that's it. Just those compounds and their reaction. Everything else is the surroundings. And so this 1 mole of CH4 and 2 moles of O2, this is the blue flame. So here is your system. It is the flame itself. And so what we're saying is that during this reaction, the energy of the system is going from this initial state, which is marked here, we'll just call that state 1, to the second state, which is down here, which are the products. And this system is traversing from a high energy state to a low energy state, which means that there's going to be a net delta E that's negative. And we see that here, right? We're starting at high, we're ending at low, we get minus 802 kilojoules. the minus indicating that we went downhill in energy. The system, in this case the flame, is losing energy to the surroundings, meaning it's dumping it. It's got to get rid of it as heat. And so all of this energy now is going from the flame itself to the surroundings, which is everything. That could be the pot that you're trying to boil some water. It could be your hand if it's in proximity. It could be just the general air molecules around it that are not part of the system. So a couple things to note here that are really important. So we're gonna walk through a lot of these examples where we're given a delta E, and note that this is given in just kilojoules. So it's just energy. It's not energy per anything, energy per gram or energy per whatever. What's implied by this this reaction or this change in E for the balanced chemical reaction here of burning methane or combusting methane is that is the total energy that the system will lose in the form of heat for the reaction as written. And that may sound confusing, but this, I'm just going to emphasize this. This is for the reaction as it is written, which implies that for every 1 mole of methane that's burned, we're going to liberate 802 kilojoules of energy. Meaning over here on the product side, we'll get 802 kilojoules for every 1 mole of this that burns. We could also think about it from the perspective of oxygen. We could say that we get 802 kilojoules for every 2 moles of oxygen that are combusted in this reaction. Or we could think about it from the product's perspective. We could say we get 802 kilojoules for every 1 mole of CO2 that's produced or every 2 moles of H2O. So it's important to note that they're not explicit about what this 802 kilojoules refers to, but it's implicit in that it's always connected to a balanced chemical reaction. So whatever the energy is that's assigned, that's for the reaction that is written, and you could think about it from the perspective of any one of the individual reactants or products, and we'll do both in this chapter. Okay, so another thing that's important to note is that this change in energy, this delta E that we have written here, this depends only on the chemical identity, the sample size, the temperature, pressure, etc. But what's important is that it does not in any way depend on how this system got from initial to final. That's a little confusing. So let me explain that. So when I say that this delta E, the change in energy of the system, doesn't depend on how it got there. What I'm talking about is this purple line, right? We have an initial state and a final state, and the difference between those is the delta E, right? That's as simple as it gets. But let's think about an alternative scenario. This line is really telling us that we've got this nice straight downhill reaction and that there's no alternative states that it exists within. That may be true, but it might not be true, but it doesn't matter. It doesn't actually dictate at all what the overall delta E is. Let's think about this hypothetical scenario. Let's say that from methane to CO2 and water in this reaction, actually it goes through several intermediates, and some of those intermediates are higher or lower energy. Doesn't matter. In the end, it still ends up with CO2 and water, and the overall delta E is still the same. And so when we talk about delta E, or change in the internal energy of the system, like this, the chemical system, it's important to note that it doesn't matter about the path that it took to go from the initial state to the final state. We don't care, because the change is all we care about. And the overall change tells us the difference between the reactants and the products. We call this delta E, we call this state function because it only depends, the overall change in the energy of this chemical system only depends on the initial state and the final state, and not at all on the path that it took to obtain those two states. Let's think about this from a totally abstract example, non-chemical, from a textbook. So let's think about this initial and final state that we just talked about for methane. So this dot and this dot. Let's think about those as two different destinations on a map. And one of them is this place in California here, and the other is Boston, Massachusetts out here. Totally analogous to this state 1 and state 2 of the chemical system, but now we're relating it to just physical places. You can imagine, right, that there are more than one way of getting between these two places. You could charter a flight and literally fly directly from Castroville, California in a straight line, which is this black line, all the way to Boston. That would be one way to traverse from initial to final, and that would be analogous to this sort of straight line, right? Simplest possible way. Or you could think about the driving. And these two green lines show you two different ways that you could potentially, of the million ways that you could do this, you could go the northern route and drive all the way up here through North Dakota and then across through Canada, or you can go all the way down here to, say, New Orleans and then way back up to Boston. When we talk about state functions, we think that the property that we're trying to measure, in this case like the delta E, it doesn't matter which route you took to get there. The actual position has changed, and it doesn't matter whether you took the northern route or the southern route or the direct route. The actual position between these two locations is still the same difference, right? You can imagine, though, that there are things that are non-state functions, things that do depend on the route that you take, and those are called path functions. And we're not going to talk a whole bunch about them in this class, because really what we want is to define a state function, and then we're going to utilize properties that are unique to state functions to help us account for some energy tabulation later. But I'll give you just a sense. So path functions could be in the case of this example, maybe the actual position as state function, you know, that doesn't change. But some things that are a function of the route that you took would be like the work expended. So the work required to get from Castroville to Boston totally depends on whether or not you drive all the way up into Canada and back down, or you take a direct route. It could also, you know, another path type function could be the amount of dollars that you spend getting between these two places, right? It could cost you totally different amounts of money depending on the path by which you took to get. Let's think about a real chemical example now. So the chemical reaction that I have up here, it might look familiar here. This is C6H12O6. This is sugar. This reaction probably looks familiar. This is the combustion of sugar, so with oxygen to make CO2 and water, right? We know combustion is always going to look like this. There's a couple different ways that we can do this reaction, right? We could do this via combustion. So we could just take some sugar and we could burn it in oxygen and we could produce this stuff. And that's going to produce this amount of energy, which is minus 2,810 kilojoules. Right, that's the amount of energy. Quite a large amount, because you've got this big chunky molecule, lots of bonds. We're going to break it apart and we're getting quite a bit of energy out of that. But you also know that your body does this right now. Anything that you've eaten in the last couple days, this is going on inside of your body, but we're not burning this, right? We're not combusting it in the same way. The same exact chemical reaction is occurring, but we're doing this metabolically. So our metabolism is doing this via a cascading chain of biochemical reactions. If you go on to take biochemistry, you'll learn all about the different cycles that take this molecule and convert it ultimately to these. Coincidentally, That's why you breathe oxygen, right? Is in order for this metabolism to work, you are intaking oxygen and you are expelling the CO2, right? This is respiration. Reaction is identical, whether or not you do it via a combustion route or a metabolism route. So you can imagine, if we were to think about this in terms of energy, we are starting with sugar and we are ending with CO2 plus water. And if we take, say, the combustion route, that's going to require a whole bunch of energy to begin with and maybe ends up here. And if we do the metabolism route, that's not going to take the same path. It's going to go through a whole bunch of intermediate pathways to get down. But in the end, the change from sugar to CO2 and energy is going to be exactly the same. And that's why we call this a state function. The change in energy doesn't matter how you get there. It just matters the difference between initial and final. And that's really useful, right? Because it allows us to think about these two completely different processes, but we still know that the change in energy is the same. This is going to be really helpful for us in tabulating energies going forward.